Okay, good morning Year 10 and welcome to today's geography lesson. So, I'm going to do something a little bit different today. I'm going to talk you through the lesson. We'll have an opportunity to pause it at different points for you to complete activities to consolidate what we're talking about. So we're going to leave the plate tectonics, plate boundaries and earthquakes part of hazards behind. I'm going to move on to look at atmospheric hazards, so hazards that happen in the air. And in particular, we're going to look at tropical storms. But in order to do that, we need to have an understanding of this model, the global atmospheric circulation model. Now, this model, essentially, if we break it down, so world, global, atmospheric, the air, circulation, so a cycle, is the world air model. Okay, and in particular what it does is it looks at how air in the world transfers heat to different parts of the world, from the equator to the poles. And what we need to do is we need to be able to explain this model. We need to be able to explain how it forms tropical storms or hurricanes, as you might know them. But we also come back to it next year when you look at ecosystems, and it helps us explain why we get tropical rainforests at the equator and why we get hot deserts at about 30 degrees north. And to do this today, we need to break it down into 3 sections. For the first one, we're going to look at latitude. Okay. Now, you'll have heard this all the way through your geography lessons from Year 7 all the way up into Year 10, but you might not know specifically what it is, so we need to know what that is first of all. The second element that we're going to look at is something called solar insolation. And this is the radiation from the sun that the Earth receives. And then the third part is air pressure. So you might have heard of high and low pressure, you might have watched the weather forecasts on the news and hear people talk about high and low pressure. We need to know what they are. And when we've got these 3 elements, we will be able to explain the global atmospheric circulation model, the way that the air moves around the world transferring heat. So we're going to start with latitude. What I'm going to ask you to do is to listen to my explanation, watch the diagrams, and then you can pause the video when I tell you to complete the task. So don't worry about writing down whilst I'm talking. You just focus on listening and watching, and then you will have the opportunity to pause, to reflect, to do some activities with the information that I am talking to you about. So the first bit that we are going to look at is latitude. Okay. Now, latitude is the angle between the equator and the North and South Pole. And when we think about latitude, we might have heard of key lines such as the equator. So let me just draw a little world, like so. Okay. And the equator that we know is in the middle, and the equator is at 0 degrees. Okay. Now, as I said, latitude is the angle between the equator and the North Pole and the equator in the South Pole. So if you look at the angle that's created, we can see that both of those are right angles. So the South Pole is at 90 degrees and the North Pole is at 90 degrees. But at this point, we don't know which is which, because if you just had 90 degrees line of latitude, someone will ask, well, do you mean the North or the South? And so we have to make sure that when we're talking about lines of latitude in the Northern Hemisphere, we make sure that our angle has an N after it. And when we are talking about lines of latitude in the South, then it needs to make sure that we have an S after it. Now, we might have heard of other lines of latitude. You think back to last year when you did some work on deserts and tropical rainforests, you might have heard your teacher mention the Tropic of Cancer and Capricorn. These are found at 23.5 degrees north for the Tropic of Cancer and 23.5 degrees south for the Tropic of Capricorn. So let's have a look and see if we can plot those on. So if we go like this, that's 45 degrees, because that's halfway through our right angle. Obviously, if I had a protractor, I'd be doing with that, so it's a little bit inaccurate. And then halfway between 45 and 0, we're going to put 23. So here, 23.5 degrees north, and that's the Tropic of Cancer. And I need to do the same in the south. I'm going to do my 45, which is there, halfway between that, 23.5 there, 23.5 degrees south, Tropic of Capricorn. Fantastic. So, we have now our lines of latitude, the most important ones. You'll see them going like that around the world. Okay, they're the horizontal lines. And they give us that angle between the equator and the North and the South Pole. So what I would like you to do, you've got 2 tasks for this section. 1, I would like you to tell me what is latitude. Okay, so the definition, what is latitude? And number 2, underneath that, sketch and label the diagram to show lines of latitude. Okay, so you might just want to put a north pole here and a south pole here. So pause the video now and complete those 2 tasks. What is latitude? Sketch and label the diagram to show the lines of latitude. Fantastic. So you've completed task 1. We've looked at what latitude is. We're now moving on to look at solar insolation. So this is solar, the sun, and in particular, it's a measurement of the amount of solar radiation that reaches Earth from the sun. And because it's a measurement, we need to know how to measure it. And it's measured by per centimetre squared per minute. So the amount of solar radiation that comes from the sun and heats an area of land per centimetre squared per minute. The sun sends the same amount of radiation to Earth no matter where you are, but where there is a smaller surface area, then temperatures are higher. So if you have more solar insolation, you have a higher temperature. Whereas if you have less solar insolation, you also have a lower temperature. So let's have a think about that. So we need to draw a circle to show the Earth. We need to make sure it's a circle. And we need to draw a slightly bigger sun, because we know that the sun is bigger. And what we can see is that the Earth obviously is a set distance away from the sun. And a common misconception, something that I don't want to see anybody writing down, is that the poles are colder than the equator because the sun's rays and sun's radiation has to travel further. Now, technically, you are correct, but that distance difference between the equator and the poles is so tiny in the grand scheme of things that it actually has no effect whatsoever. And the biggest reason why there's a temperature difference between the equator and the poles is because of the curve of the Earth. Okay, so let's have a look at what that means. Let's start at the equator. So let's imagine. Okay, this is the sun's solar insolation, all right, hitting the Earth and heating the Earth. And what we can see if we look, the solar insolation is concentrated. It's concentrated on a really small area. That area there is the area that's being heated by our solar insolation. So at the equator, our solar insolation is concentrated. Okay, which means that it has higher temperatures because the surface area it's heating is lower. Okay, smaller. Let's have a think about the poles then. So let's do the same. There we go. Same amount of sun hitting the poles. And what you'll notice straight away is that area between the sun's insolation is much larger. And that's simply due to the curve of the Earth, curvature of the Earth. And because it is larger, so the area per centimetre is much larger, that means that the sun is less concentrated. It's spread out over a larger surface area, which means that temperatures are cooler. So let's summarise. So poles, same amount of solar insolation. Okay, that's important. No matter where you are on Earth, it's the same amount of solar insolation, but it's spread out over a larger surface area. This means that it is less concentrated. And because it is less concentrated, this leads to lower temperatures. Okay, so it's the same amount of solar radiation to any part of the world. It doesn't matter. It doesn't matter where you are, the sun is sending the same amount. But what does matter is the concentration, and that is determined by the curvature of the Earth. At the poles, it's really concentrated, so we have high temperatures. At the poles, due to the curvature of the Earth, it is more spread out, so it's less concentrated and you have lower temperatures. So, what are you going to do? Okay. Your first task is to tell me what solar insolation. What is solar insolation? Number 2, how is solar insolation measured? Number 3, why is solar insolation higher at the equator than at the poles? Okay, and then think about what impact does this have on temperature. So what you're going to do now is pause the video and complete those 3 tasks. Okay, once you've done the tasks, unpause the video and we'll move on to the 3rd section, which is air pressure. Okay, welcome back. So, to recap what we've done so far, we've looked at latitude, the angle measurement between the equator and the North and the South Pole. We've looked at solar insolation, so looking at the concentration of solar insolation, how that's affected by the curvature of the Earth. And all this combines with to tell us essentially that at different latitudes, locations have different temperatures. Okay, and what we need to do now is to look at this idea of air pressure. Okay, and air pressure is the weight of the air, gases, above us, which is all held in place by gravity. So let's break that down. So in the atmosphere above us, we know that it is filled with gases. Okay, and those gases are held in place by gravity. And if we take the second part of that, pressure, okay, we know that when something's under pressure, all right, it's the weight or the force of something pushing down, which in this case is the weight or the force of the gases. Now, as I mentioned at the start, you might have heard of high and low pressure when you watch the weather. And typically, most people think that high pressure is warm, sunny weather, all right? But that's not true. It doesn't always mean warm, sunny weather. Same for low pressure, it doesn't always mean cold weather. And so what we need to do is we need to think about, well, what actually happens in areas of low pressure and what happens in areas of high pressure. So, let's take our Earth's surface. Here we go. Okay, remember you don't need to copy anything until the end when I set you your tasks. So, if we've got low pressure, all right, that means there's not a lot of pressure forcing something down. And in fact, when we talk about low air pressure, we actually mean that warm air is rising. So when we have warm air rising or air rising, there is a lot of evaporation taking place. And as that rises as water vapour, we know that it cools. And that's because as you travel higher up in the atmosphere, for every 100 metres above sea level you go, air temperatures fall by 0.65 degrees. So that water vapour, as it travels up through the atmosphere, is slowly cooling. And as it cools, it turns back from water vapour into water droplets, condensation. And it forms clouds. And we know that when those clouds get too heavy, we have precipitation. So let's think about it. All right. Low pressure, we have evaporation, which leads to condensation, which leads to precipitation. Not just always rainfall, snow, sleet, hail, and so on. Okay, so at areas of low pressure, we tend to get high rainfall. Okay, so we need to contrast that now with high pressure. So when you've got high pressure, that means that the air is falling. Let's go a little bit lower towards the Earth's surface. There we go. Not high. So our air is falling. The air is pushed down. And where you have the air falling, there's not a lot of evaporation. So in fact, we have less evaporation, which means we have less condensation. And as a result, less precipitation. So you have very few clouds, very little rain happening here, because there's not as much evaporation taking place. So when we think about this in terms of last year, when you looked at tropical rainforests often occur in areas of low pressure because they need a lot of rain to survive. Whereas higher pressure areas tend to be deserts, whether that's a polar desert or whether that's a hot desert. Okay, so what I would like you to do for your task in this section is, number one, copy this diagram here. So you know the characteristics of low and high pressure. Make sure that you add the labels down the sides. You might want to add some additional explanation in a moment if you want to. I want you then to tell me what is atmospheric pressure. So remember that atmosphere is made up of the gases that are held in place by gravity, and the pressure is the force of those gases pushing down. And then I would like you to tell me what weather conditions are found in areas of low pressure and why. And then the fourth one, repeat number 3 for high pressure. So what weather conditions are found in high pressure and why. Pause the video now, complete those tasks. Once you've come back, what we're going to do is going to put all of it all together to explain this idea of the global atmospheric circulation model. Okay, so our final step is now to put it all together. We've got the idea of latitude, we've got solar insolation, so we know that different places in the world have different temperatures depending on their latitude, and we know what high and low pressure are. Now, as I said at the start, the global atmospheric circulation model is the model which shows how air distributes heat around the world. And what we need to remember is that it is a mirror between the north and the southern hemisphere. I'm only going to explain it for the north, and you're going to have a go at doing it for the south when we finish. So we have exactly the same in the southern hemisphere as it is in the northern hemisphere. Now, let's start at the equator. And at the equator, we know that solar insolation is high. So it's concentrated. We have high temperatures. And at the equator, we have low pressure. And the reason why we have this is because warm air is rising. And it rises to that top layer of that part of the atmosphere. It's called the troposphere. You don't need to remember that. It's just good to know. And it can't go any higher. It's at the ceiling limit of that part of the atmosphere. And so it spreads south and north. Okay? And as it spreads north and south, it becomes a little bit cooler. And we know that when things cool from being warm to cold, they become denser. And so it sinks. And it sinks at 30 degrees north. So here we have areas of low pressure, and we've got warm air rising, so high amounts of evaporation, high amounts of condensation, high amounts of rainfall. Just going to draw a little rain cloud so that we remember that. But here, air is falling. And we know that when air falls, we have an area of high pressure. So here we have sunnier weather with very little rain and very little cloud. And what we need to think of, well, we've only got a partially completed cycle. It says it's a circulation model, so circular means it's got to go round and round. And what we have is along the Earth's surface, to blow the warm air back from high pressure to low pressure, is something called the trade winds. And the trade winds, what we're going to come back to when we look at tropical storms, is they help us to explain that. And in the northern hemisphere, they all veer towards the right because of something called the Coriolis effect, which is the spin of the Earth. So we have the winds moving that way. But don't worry too much about that. We'll come back to it when we do tropical storms. So we have now our first cell, our first atmospheric cell. At the equator, we've got concentrated solar insolation, which leads to warm air rising, which is low pressure. So we have high amounts of evaporation, high amounts of condensation, high amounts of precipitation, which means we've got lots of rain. Whereas as that warm air rises, it cools, it starts to sink because it's falling. So we've got high pressure. So we have sunny weather with less rainfall and less clouds. Now, whilst the trade winds blow the warm air from high to low pressure, we also have winds blowing this way because it always blows from high to low. So because we've got high warm air blowing from 30 degrees to 60 degrees, it meets colder polar air. And when these two air masses meet, the colder air is denser. So it forces the warm air to rise. So I think it's exactly the same as down here. We've got warm air rising. So at 60 degrees north, we've got our rain again. Okay, and we know, same as here, when it reaches the top layer of that atmosphere, it spreads south and it spreads north. And at the poles, we know we have high pressure, so we have air falling. Draw a little sun again, because we've got less evaporation, less condensation, so we've got less precipitation. And that is our tricellular model. We've got 3 cells, tri is 3. And each of these cells have their own names. So this one is called the Hadley cell, and it's the biggest. This one is called the Ferrel cell, it's the second biggest. And this one is called the Polar cell, and it's the smallest. And this helps explain how the air distributes heat around the world. You can see warm air blown meets the cold air coming down. So this is mirrored in the southern hemisphere. It's exactly the same. And what we need to remember is that as we travel northwards and southwards from the equator, temperatures decrease. So temperatures decrease as distance from the equator increases. Okay, so before I set you off on your task, I'm just going to go through that again. So at the equator, we have high solar insolation. That leads to high temperatures, which means we have warm air rising. Where we have warm air rising, we know from our previous exercise that that's a low pressure. So we have warm air rising, water vapour within it, we have lots of condensation, lots of precipitation leads to rainfall. When it reaches the top layer of the atmosphere, it spreads north and south. And as it spreads north or south, it starts to cool, it condenses, it becomes heavier, so it sinks downwards. And we've got falling air, which means we have high pressure, which means we have less evaporation, less condensation, and less precipitation. Now, because this is a cycle, our air has to travel back towards the equator, and it does that by something called the trade winds. And the trade winds blow, in this case, from 30 degrees north to the equator. And the winds always blow the air at the surface from areas of high to areas of low pressure, which explains why at 30 degrees north we have some of that warm air travelling upwards towards 60 degrees north. But it meets the cold air coming down from the poles, which is also an area of high pressure. And when the cold air meets the warm air is forced upwards because it is less dense than the colder air coming from the poles. And where we have air rising, warm air rising, that means we've got low pressure. So we have again evaporation, condensation to form clouds, and precipitation. And when it reaches the top layer of the atmosphere, it spreads south or it spreads north. We go north, the air then starts to fall, so we have high pressure, which means we've got less evaporation, less condensation, and less precipitation. So, what would I like you to do? Your first task is to sketch the diagram. So I want you to sketch the Earth, label 0, 30, 60, 90 degrees north, then draw the cells and put low, high, low, high. I would then like you to complete the diagram for the southern hemisphere. Remember what I said at the start, it's an exact mirror image. Once you have done that, I would like you to explain what happens in the Hadley cell. I want you to explain, essentially, why do we have air rising? What happens when it gets to here? What happens as it travels north? What happens when it sinks? What weather conditions do we get here? And then why does it get blown back towards the equator? Okay. Also, include at 0 degrees and 30 degrees north the weather conditions. So explain what happens, the movement of air, and then tell me about the weather conditions here and the weather conditions here. Okay, and that concludes this section of hazards, looking at the global atmospheric circulation model. As I said at the start, take a picture of your work, upload it onto Microsoft Forms, or email it to your teacher so they can just check through. Well done for listening and completing this section.